watching this computer where there's a UV chromatogram that is going to show me when the protein is coming off of the purification column and into the fraction collector. And so because protein absorbs UV, you'll see a peak on the chromatogram. And so today I just want to do a quick post about how we interpret chromatograms and why I'm looking for that nice sharp peak. Okay, so it ended up being not so quick, but I go through the basic overview of how to interpret one of these, and then take you more detail and practical stuff about like how to work with the software and interpret the various things to look at during one of these runs. So I just thought as I was going through it, I would just share a more practical thing for people who wanted it. So you were looking at an AKTA machine, which is a type of fast protein liquid chromatography. So with any type of protein chromatography, our goal is to separate proteins based on their different properties by taking advantage of how those properties make them interact differently with different types of resin, or these little beads that we fill these columns with, and then we flow a mix of proteins through the columns, and then the proteins will interact differently with the different types of resin. And this is going to allow you to separate the proteins based on things like specific tags, or based on their charge, or based on their size. And so much more in protein chromatography and other posts. But the readout when you're doing one of these chromatographies, if you're using one of these AKTA machines, is you're going to get some sort of chromatogram. So basically, this is going to show you where proteins are coming off, and it's going to be able to detect the proteins based on their UV absorbance. So as the protein is coming off of the column before it goes into like your fraction collector, so before it goes into the part where you can collect it in tubes or blocks or wells, various size tubes and things, that it goes through this UV detector. And the reason why this is helpful is because proteins absorb ultraviolet light. So what I mean by a chromatogram is something like this. So it's going to basically show you the UV absorption on the y-axis and the time or the volume that's come off. So the elution volume is going to be on the x-axis. So as proteins are coming off of the column, they're going through a UV detector. Proteins absorb UV light, and they absorb highly at 280, which other things don't absorb at as much. You have a more specific signal from protein at this 280, corresponding to the absorbance from primarily tryptophan, but also some from phenylalanine and tyrosine, these aromatic rings. And so by measuring this UV absorbance, we can get an idea about when our proteins are coming off of the column. And by doing this right before they're going into the fraction collector, we can then collect those fractions and know which fractions corresponded to when the protein was coming off. So when we're looking at a chromatogram, if we're looking at the UV absorption, so like UV 280, if we have something in this y-axis, this is going to tell us about the amount of protein, like so how much it absorbs is going to be like related to how much protein there is. So the more protein, the higher the absorbance. Although I should note that this is going to be specific for different proteins. So some proteins, because they have more of those like tryptophans and stuff, they're going to absorb higher. The same amount of protein is going to absorb higher because they happen to have more of those amino acids. And so you can use a tool like UniProt to get the actual like extinction coefficients, and you can actually use that to quantify the amounts of protein. But I'm not going to go into that in this post. But so basically, the higher the peak, the more protein there is. And the sharper the peak, typically like the purer the protein is, it depends on the method. So when I'm doing like a size exclusion, which I'll tell you more about later, there you really want a sharp peak because you're separating things by size, and then you want to have the things that are one size are going to come off at one place, and things that are another size are going to come off at another place. But if your things are really closely sized, then their peaks can kind of overlap. Or you can get this broad peak that can kind of contain a lot of different things. So sharp peaks are good, and they're also easier to collect and concentrate and do whatever you want to do afterwards with them. When you're looking at one of these chromatograms, typically you'll have some sort of column equilibration step.
So if we're talking about chromatography methods, a couple of the main ones are like affinity chromatography, ion exchange chromatography, and size exclusion chromatography. I'll show you more of an example with size exclusion later, but for affinity or ion exchange, here you're actually getting a protein stuck and then unstuck. And so based on like the protein actually binding to the beads. Whereas with size exclusion, you're just taking advantage of the fact that different proteins are going to flow through these beads at different rates, because the small proteins are going to have access to all these little pores in the beads. They're going to travel slower because they have to travel a further distance than the big proteins, which can kind of just go around or go through fewer of these tunnels. So we can have different types of elution. So elution is where things are coming off. If we're doing size exclusion, we're not changing our buffer. And so we just have an isocratic elution where we just have a single buffer. But for other methods, we're often combining buffers, we're mixing buffers. We can do this in a gradient or a stepwise fashion where we can introduce a competitor or like higher salts, change the pH, various things. Typically you have your buffer A and your buffer B, and like either can be either, but typically your buffer B is going to be your higher salts or your competitor, that sort of thing. And so you can increase the percent B, and then you can actually plot this on the chromatogram. But first you want to whatever your method, you're going to need to basically equilibrate your column. And so this is before your protein even like goes onto the column. You need to make sure that the column is going to have a steady baseline. And if you're doing something with like a competitor or whatever, you want to have a low level of the competitor or salt, just enough to prevent non-specific binding. Then you're going to load the sample. So you basically put your sample onto the column. And then so some stuff is going to bind to the column. And then you're going to just like stuff that some of it will be your protein. So this is if we're talking about affinity or ion exchange here. Some of it'll be your protein, some of it won't be your protein. It'll just be like non-specific stuff, but then you can do a column wash. You wash at a low level of competitor or salt to remove the non-specifically bound stuff or the weakly bound stuff, and then you start the elution. So you can do this gradient dilution where you basically gradually increase the percentage of B or whatever. So you have your higher salts is gradually introduced to your competitor, like imidazole or just thiobiotin is gradually introduced. Or you can do stepwise where you just do it all at once. With stepwise, you're more likely to get just like a single peak because you are just doing this way. If you have a really pure sample, this can be useful because you can get typically like if it all comes off at once, you can kind of get like a sharper peak, but it can have more things inside of it. Whereas if you do a gradient dilution, you're more likely to separate out things that are differently charged or differently affinity bound or whatever. So you can have better separation, but you're likely to get like this broad peak that you're then going to have to like concentrate down. So this would be like an example of a gradient dilution, and this would be an example of a stepwise dilution. Either way, your protein should hopefully be coming off here, and then you can look and see which fractions it came off in, and then collect those fractions and work with them. So for some sort of like affinity or exchange or ion exchange, basically there, your volume, like your elution volume, is going to correspond to how tightly the thing was bound. So in the case of like an ion exchange, it would be how oppositely charged is it. So if you have a positively charged resin, you have a negatively charged protein, the more negatively charged it is, the stickier it's going to be, the more salt it's going to take to elute it off. Similarly with like affinity chromatography, the more stuck your thing is, the more it's going to take, more of the competitor it's going to take to come off. And so things that are really well stuck are going to come off later than things that aren't as stuck on. And so with ion exchange, this is going to allow you to separate things that have similar but different-ish charges. So they have similar enough that they're stuck to the column. So they're the same like opposite charge at that pH, but they have different enough charges that you can separate them by differential amounts of salt. In a chromatogram for a size exclusion chromatography, here things are different. Here you're separating based on size. And so bigger things are going to travel more quickly because they're going around the bead's pores, or at least through fewer of the pores. And the smaller things are going to travel more slowly because they have to travel through all of those little pores. And so they have to take a longer path. So then they're going to come out earlier. And so there's different things but there's different information that can be gained by looking at the elution volume. And in any of these cases, note that it's showing you like a protein is coming off likely, but not necessarily what the protein is. And so the next step is typically to do an SDS page. And then that will allow us to see like that the size of the protein, the purity of the protein. You can see if you actually have a lot of different proteins inside of that one peak that look really nice. But typically, like if you have a nice symmetrical peak, that's a good sign, especially if it's like in the size exclusion chromatography. If you have a nice symmetrical sharp peak, that's what you want to see. And that's also a good indication that your protein is nicely folded. When you do like an SDS page, you're denaturing all the protein. And so then you can't tell if your protein was actually present in like some insoluble clump or it was this weird misfolded thing. But if you have a size exclusion chromatography one where you have this nice sharp peak, that's a good indication that your protein is happy and well behaved. And hopefully you have some sort of functional tests that you can do as well if it's something that if you made a mutation or something you want to test that it's actually functional as well. But you always want to see that nice sharp peak. And so let's look a little more about how it in practice and show you some of the stuff, how to work with the AKTA software, as well as it'll be similar if you have other software as well, but the basic things to look at in a chromatogram and various parameters to keep an eye on during a run. So this is like the unicorn software that we use with the AKTA machine. And so I'm using an AKTA Pure. There are different types of AKTAs and there are different things. Some of them have only like our AKTA Explorer or whatever, we have manual control. You can do things manually here as well, but you can also set up methods. So I do not work for the AKTA people, but they have really great customer service I found and a really great, so thank you. But this is the software that comes with it. And so a lot of people use AKTAs. And so I figured that this would be helpful for other AKTA users, as well as the information about the various chromatograph things that will be the same, even if you're using sort of different system, although you might have to find how to change the parameters a slightly different way. But so this is the system control. And then if you go to tools, you can also go to like the method editor where you can design automated methods, and the evaluation where you can look and see where things are, as well as column handling where you can get the specs about specific columns. So I was super excited that my protein came off in the place I would expect it. So this is a size exclusion chromatography run. So I'm separating proteins by size. And based on the protein size, you can kind of like estimate where it should come off of the column. And this peak is consistent with what I would expect based on previous experiences with this protein. And so although it's by like size, it's kind of by shape too. So if you have a really floppy protein, it's going to run a lot like it was a lot bigger than it actually was. Because this is a size exclusion chromatography, and smaller things are going to have to go through more pores. They're going to go slower. Bigger things are going to go faster. So bigger things are going to come off first. So they're going to be more to the left. So I have this set to, so these would be things that are bigger than my protein of interest, and things that are smaller, my protein of interest are going to come off over here. A word of caution is that I was watching this really closely and I kind of panicked a little when I saw things start to come off earlier than I would expect, but those were just contaminants. And so these little humps you can see are contaminating proteins and or like clumps of proteins potentially. And so I'm glad that I was able to separate them from my protein of interest, or what I assume is my protein of interest, based on the gels and the size and everything, and the fact that I purified it with affinity chromatography first. And so I took advantage of a recombinant tag on the protein. So I specifically purified it. So then, because I'm doing this, I have these lines are representing the different fractions. So I have it set to collect 1/2 ml fractions. And so I can then take the fractions that I want. So basically after it goes through the column, it's going to go through into this fraction collector, and it's going to collect the fractions. And I have it set to collect the 0.5 ml fractions in this 96 well block. And so then I can go take the fractions that correspond to the protein peak of my interest and And then I can pull these and concentrate them and freeze them down because this is my last step. If I wanted to do other things, I could do other things and also run a gel. If I wanted, I could run gels like an SCS page gel to see, make sure it all looks pure and nice. I could also test these to see what these were, or at least what size they were and that sort of thing. The good thing is that the peak of my interest seems to be isolated from the others, and it's fairly symmetrical. Sometimes you get weird, like bumpy peaks where you have contaminating proteins. You can kind of get like a shoulder, or you can have problems with your peaks. But a nice symmetrical peak is what you want, and hopefully so that you can isolate it from the other proteins that came off the column. So I have this axis set to milliliters. I like to leave it in milliliters, but if you click on it, you can go to minutes. Sometimes this is helpful if you're trying to see how long to expect before your next run, that sort of thing. So this is actually my first of 2 runs. So I'm waiting for it to finish before I start, before I do the second run. And so I need this because of the size exclusion, but basically you need to have everything come off of the column before you start your next run. And it's not like a technique where you can just do a high salt or high competitor to push everything off, because with size exclusion, you have this constant buffer and things are just moving through by size. And the smallest things are going to take the longest to get through the column. And the longest that they could take is 1 column volume. So if you look, you can actually look up the column volume for your specific column. So I'm using this SuperDex 200 increased 10300 GL. You can see that the column volume is 23.562 mils. So basically 24 mils. And then everything should be through. Although typically you want to also look at the baseline to make sure it's steady. But so it's a little deceiving here because the 24 whatever, that's after you inject. So you have to take it from when you injected. And so when I injected, it was actually here, this injection mark, this like pink line. So basically I started the run, then I filled the loop, bypass, so it didn't wash the loop, and then did a manual next step, so it'll start that. And so here it was injecting onto the column, and then here, this part where nothing's happening, like where you don't see any change in the signal, and you also don't see any fractions being collected. That's because I have it set to not collect fractions in this first portion, which represents like the void volume. So this is basically anything that was in the column before, or anything before I injected, or anything that was so big that it just went straight around to all the beads. So something like an aggregate would come out in the void. Also, like the beginning of this can sometimes be some of the void as well. But you can see that so I have it set to start collecting fractions after the void volume, and to have it collect these small fractions so that I can get better resolution. So the downside of doing the small fractions is then you have to like pipette out, combine a bunch together, but at least you can then better isolate these. So if these had been bigger fractions, it would have been harder to separate the peaks without losing my protein. So I have it set with to monitor 2 wavelengths. So I have the 260 and the 280. So this is often good, especially if you have a protein that binds to nucleic acids, or you suspect it might bind to nucleic acids, so like DNA or RNA, because they also absorb UV light, and they actually absorb UV light like really, really well. So if you have a protein that, like I study a protein that binds to RNA, I'm purifying a different protein today, but when I study that protein that binds to RNA, then I get a really high peak, but it's kind of deceptive because it's corresponding to the RNA mostly. But because nucleic acids bind at 260 a lot more than they bind like predominantly 260, even though they also absorb at 280. By measuring the 260 and then looking at the 260 to 280 ratio, you can see if things are like nucleic acids versus proteins. So if I had the 260 was like a lot higher, then it would tell me that I had, like if 260 was higher than 280 or whatever, then that would represent a nucleic acid, and you can have like some ratio between the two. You'll also sometimes see stuff come off at the end, which I really have no clue what it is. It just like, if you run a gel of it, you can't see anything. So I think it's some sort of salt or something. I really just don't know. But what else can we look at? So basically, when you have, I had to pre-equilibrated the column. So I did it like overnight. So that, and typically I pre-equilibrate it with like a column and a half's worth, or at least, or actually like 2 columns worth. You want to make sure that you get a really steady baseline. So basically you want to make it so that your 260 to 280 ratio is constant, your conductivity is constant, everything is constant. So before you actually start the run. And so you can have the run set so that you have, it has an equilibration built into the method, but you can then bypass it if you've already pre-equilibrated your column. So then you have the void volume, then you have the sample collection. And so this, you can have the, you can set the display to display different things, and there are different things that are helpful to monitor during the run. You can also see some of these things down here. So this pre-column pressure and delta column pressure, these are going to be specific for the different columns. So different columns have different pressure limits. So the pre-column is like measuring the pressure going onto the column. And if this is, if you have problems, so the delta column is going in and coming out. So if you have problems like getting through the column or whatever, you're going to have this buildup, and you're going to have this problem. This is going to show up in your like delta column pressure, and you have alarms built in or settings built in that it's going to stop the run if it has this. If you're doing a manual run, you have to set these limits yourself. So you can go to manual, execute manual instructions, and then you can set like alarms and do the pressures. And you can find that information in the column handling as well. So when you are doing this, but when you have your main, when you do like a method editor and you set up the runs, you tell it what type of column and stuff and the pressure limits, and it will do this. In terms of start protocol, I also like to include the variable list so that you can change the column and the loop and everything instead. And you just have like a flow rate, %B, because this is if you had a buffer A and a buffer B. So if you're doing some sort of like stepwise or gradient elution, you would see that would be more interesting. But here it's not, because we have a single buffer, which we call an isocratic elution. So in addition to the pressure, the pre-column pressure and the column pressures, we can also look at the system pressure. So if I go to filter curves, if we look at the system pressure, so we can see that you have the system pressure changes when you like changing a block or whatever, but it should stay fairly constant, and your conductivity should stay pretty constant too. If you have like, so the system pressure, if it like goes to 0 or whatever, like if you can see problems show up if you look at the pressures or the conductivity. If you're having problems, you want to make sure that you don't have like that your pressure isn't all wonky. That could represent like if you have air in your pump or that sort of thing. Various problems can happen. And if you look at the pressure, you might get a hint as to something is off. If you have, so right now this is bypassing the pH valve, but you can set it to like actually look at the pH. But you can see, so here it's going, this is showing you like the flow path is going A1 going onto the column. When it was injecting, it was going, then this would shift and it was showing it was going through this loop. But now everything's just going straight onto the column, and it's going through a UV detector, which is how we are able to see all this. And then it is going through the conductivity detector, then it's bypassing the pH valve and going to the fraction collector. So the conductivity in an isocratic elution like this should stay constant, but if you have a gradient or a stepwise, you'll see that as you increase the salt, say, then your conductivity will increase as well. If you click on like various things, you can change what is set as what you're looking at. in terms of the y-axis. So I like to set it with the 280. So here's an example of a gradient dilution. So this was from an ion exchange. So this is a Q column. So it is an anion exchange. So it's capturing negatively charged parts of proteins. So you can see that here you have the blue line. This is your concentration of B. And so my B was a high salt buffer. And you can see that, so the conductivity is going to increase as with the salt. But you also see that as you increase the salt concentration, various proteins will come off. So this was all just like sample application. So you can see that there's a lot of protein that didn't stick to the column, which is what we wanted, because I basically want to optimize so that my protein is the main thing sticking to this column. And then you can see that as you increase the salt, then you have your protein come off the column. Here's an example of another ion exchange. This one is an S column, so positively charged cation. This one is actually a step gradient dilution. And so you can see that this buffer B, I have it set so that it does one concentration and then a higher concentration and then an even higher concentration to wash it off, so the salt. Also find, so this is what I was telling you about before, how if the 260 versus 280. So you can see that this one, this is the peak that actually has the RNA bound. So it has the 260 above the 280. Whereas here, it's just the protein RNA free. And so it has the 280 above the 260. And so then you also see that there's like this peak looks a lot nicer than this one. This one has multiple proteins in it. And so then during the size exclusion step, I can then separate those out. So this is an example of an affinity chromatography. So this was an IMAX, so an immobilized metal affinity chromatography. So this was a column that was coated with nickel, and I had a protein that had a his tag on it. And so you can see that in this case, there's a lot of stuff in this sample application. So a lot of stuff that just like when you're loading it, it's not sticking. And this is because it's this affinity tag where I have it so that only my protein should stick, because only my protein has the his tag. And so some things might stick non-specifically, and then they can come off in this like wash step. But my protein will stay on. And then when I increase the imidazole, so this the concentration of B, so my B was my high imidazole buffer. When I add the imidazole, then my protein comes off, and then I do like a really high imidazole in order to wash the column for the next person. So once the run is done, now I want to wash my loop so that I can inject the next one. So now you can see that it's going to actually change. And so now the flow path is going to go into the loop valve and wash this. And then I can set it up. Then I can go to my evaluation tool and I can look and see this. And so now you'll see that this tool has set it so that now it starts the 0 with sample application. And this is really helpful because then you can then compare the runs in terms of where we typically talk about like what mill they eluted at or whatever. You can imagine that if you were to inject your sample at different mills into the run, then you would have this time scale would be shifted, or this elution scale would be shifted. And so this normalizes them all, so you're able to compare them. So it does this thing. It's like trying to recognize the different peaks and show you the peaks. And so I would probably take a closer, finer cut on this peak, depending on how much I care about having the protein versus having to concentrate it more and potentially have some contaminants and stuff there too. But it looks pretty symmetrical and a nice peak. And so then I would take in these fractions and collect them. I can also have it show me different things similarly to how I had looked at before. And if I wanted to see things about the run record, I can see that as well. So I have this in mils, but once again, I can change it to show different things. So here I can have it show column volumes if I want, or I can have it show in minutes. Now that it is washed, I can go on to my next run. So I'm going to start the run and then I will go inject. So we actually use like VNC Viewer for this one. We use like remote desktop for the other AKTAs, but basically it allows us to remote monitor and control the desktop, which is really helpful if you're doing a protein purification, or we have our AKTA in the other room and we want to watch it from the lab when we're doing other things, or if we want to have a run going while we're like home, like if we have runs going overnight, because you can automate stuff, it's really helpful. And you want to make sure that you're able to see if everything's going okay, as well as be able to control it if you need to change anything, see when your protein's coming off without having to stand by the AKTA machine all the time. It came in really, really helpful during the pandemic when we were like working weird shifts, and you would be able to start a run and then go home while other people were in the actual lab. There's also been lots of times where I have runs set to go like overnight or whatever, and then I'm monitoring them and realize there's a problem, and so come back into the lab with my hair wet and in my pajamas to fix the run column. But yes, so it's very helpful to have this like remote viewing. So another helpful thing is you can do like right click and you can do vertical marker. And so here you're able to see like the height of the peak. It'll show you up here. So right here, whatever it was looking at here. So the volume, as well as like the absorbance units. So in this case for 280, because sometimes it can be really helpful, especially if you have it like weird at a weird zoom. And so you're able to also change the zoom level. So it looks like you barely have a tiny little peak, but then if you zoom in, you can see that your scale is very, very high. Just a word of warning, when you're doing protein quantification and you're doing a UV absorbance wavelength spectrum, here the axis is totally different. So you're still looking at UV absorbance, but here you're testing out over a range of wavelengths. And you'll see that different things will absorb more predominantly in different places. And so corresponding to basic differences in their molecular structure, and more on that in other posts. But you'll see that pure protein is going to absorb most strongly at 280 from the rings of the aromatic amino acids and 230 from the protein backbones, but also like salts and phenol and stuff. Nucleic acids are going to absorb strongly at 260, and they also absorb at 280, but they're most strong at 260. And importantly, protein is a lot less at 260, but more at 280. And so by measuring 280 and 260, that's going to help us see nucleic acid contamination in our protein preps. But the really important thing is that these types of spectrums, it's important to remember that here we're looking at wavelength. So here we're looking at different wavelengths, whereas here, when we're using a chromatogram from the AKTA, we're looking at like time or elution volume. So sometimes you have to kind of like keep switching back in your head. So you're looking at like one wavelength or two wavelengths, but there'll be different curves. And then over time or elution volume compared to looking at different wavelengths. So I'm going to take those peaks, the fractions corresponding to those peaks, and it can be hard to kind of see what's what when you're looking at a clear block on ice. So I can go and I actually use a Sharpie and just like mark around the block, so I make sure that I'm combining the right ones. I'm going to combine them and then I can concentrate them down and also run a gel to make sure that all looks okay. My protein! Aliquoted, frozen, and going in the -80.